Welcome back. I'm glad you're joining me for this next session on the stiffness method. Until now, we've developed the local matrices for trusses, beams, and frame elements. We've also learned how to input them into the global matrix. Today, we will be looking at the force vector, and that is to complete the whole stiffness equation of force equals the stiffness matrix times the displacements, so that we can finally solve for displacements. In the last few lectures, we built the element stiffness matrices, rotated them into global coordinates, and assembled them into a global stiffness matrix. But so far, we've only constructed the left-hand side of the stiffness equation. To solve it, we also need the right-hand side, which is the load vector. So in this lecture, we'll introduce the load or force vector, we'll distinguish between nodal loads and equivalent nodal loads, and we'll work our way through truss and beam examples. By the end, you'll be able to assemble the global load vector ready for solving displacements in the next lecture. The stiffness equation relates stiffness and displacements and forces. We already know how to construct the global stiffness matrix K. We will soon be solving for the displacement vector D, but before that we need the global force vector or load vector F. This vector collects all the external actions applied to the structure and represents them in a way that is consistent with the chosen degrees of freedom. Without this vector, the stiffness equation cannot be solved. External loading can appear in two different ways. The first type is nodal forces. They're loads that act directly at a joint. They're simple to place in the force vector. The second type is member loads, like UDLs or distributed loads acting on a beam. These cannot be directly placed into the force vector. Instead, they must be converted into equivalent nodal forces and moments. These equivalent forces produce the same overall effect on the structure as the original distributed load. Let's consider a simple truss. A vertical load of 10 kilonewtons is applied directly at the top node. Because this load is applied at a node, it can be inserted directly into the global force vector. We locate the degree of freedom corresponding to the vertical displacement at that joint, and we place the value there. All other entries remain 0. In the stiffness method, every action must be expressed in terms of the degrees of freedom at the nodes. If a force or moment is applied directly at a node, we can place it straight into the load vector, as we just saw. But many real loads act along the length of an element. For example, a uniformly distributed load or a point load on a span. These cannot be entered directly into the nodal force vector. Instead, we need to replace the original loading with an equivalent system of nodal forces and nodal moments. This equivalent system produces the same shear, bending, and equilibrium effects as the actual node. Typically, if a concentrated load or moment acts at a location, we would place a node there. But for distributed loads, we cannot add an infinite number of nodes. So instead, we use equivalent nodal forces and moments at the existing nodes of the element. This is the principle behind equivalent nodal forces. We always create a system of nodal actions that is equivalent to the real loading in terms of structural behavior. Looking at this beam with the global degrees of freedom noted in blue, for a simply supported beam under UDL or uniformly distributed load, the equivalent nodal forces appear only in the vertical degrees of freedom. Each end carries half of the total load, WL over 2. Because the distributed load acts downwards and our positive displacement direction is upwards, both entries at each node appear as negative values. There are no axial forces, so the U degrees of freedom are 0. And because the ends are simply supported, no fixed end moments develop, so the rotational degrees of freedom are also 0. So for a simply supported beam under a uniformly distributed load, the equivalent nodal forces appear only at the vertical degrees of freedom. We can now examine the same UDL acting on a beam with fixed ends. Because the ends restrain rotation, the load induces not only shear forces but also end moments. We keep the same sign convention as in the series. Vertical displacement is positive going up, rotation is positive counterclockwise. A downwards load, therefore, gives negative vertical nodal forces, and each end carries half of the total load. So the vertical entries are minus WL divided by 2 at node 1 and at node 2. Next are the rotational components. Under a downward UDL, the beam develops hogging at the supports. In our sign convention, this appears as minus WL squared divided by 12 at the left end and plus WL squared divided by 12 at the right end. The magnitudes match the standard fixed end moments for prismatic beam under a UDL, and the opposite sign ensures overall equilibrium of end couples. The axial entries remain 0 because a vertical UDL does not generate any axial actions in this element formulation. And putting it together, the consistent load vector for the fixed case is shown here. The vector can be mapped onto the global force vector using the element's degree of freedom indices when we assemble the structure. Here is a summary of standard equivalent nodal forces for some common cases. A point load at midspan splits evenly as nodal forces at each end. A uniform load on a simply supported beam becomes nodal forces only, each of minus WL divided by 2, and a uniform load on a fixed beam produces both nodal forces and end moments. These standard cases are widely used and form the basis for most practical load representations in the stiffness method. Let's work through a numerical example and introduce some numbers. We have a beam with a length of 6 meters and a uniform load of 10 kilonewton per meters, which gives us a total load of 60 kilonewtons. Each end therefore carries half, minus 30 kilonewtons in the vertical degrees of freedom. The fixed ends also resist bending, producing end moments. The fixed end moments formula gives us WL squared divided by 12, which is 30 kilonewton meters. At the left end, this appears as negative, and at the right as positive. When we assemble the global force vector, the process is very similar to assembling the stiffness matrix, but there is one important difference. We start by identifying the global degrees of freedom ordering, and then for each element we calculate its consistent load vector. We then place those entries into the correct positions in the global vector according to the element connectivity. But unlike the stiffness matrices, the load vector does not need to be rotated or transformed. All loads are defined and assembled directly in the global coordinate system. And this is because the loads we apply, such as nodal forces, distributed loads, or equivalent nodal actions, are always described in global coordinates from the beginning. So the global force vector is built up directly with no need for transformation. This is an important simplification compared with the stiffness matrix. Before we move on to coding, let's quickly look at some common pitfalls. The first is forgetting nodal moments in beam and frame problems. The second is placing forces in the wrong degree of freedom position. Another issue is sign errors, using the wrong sign convention for vertical forces or nodal moments. And finally, sometimes loads are mistakenly applied in local axes instead of the global axes. These are avoidable mistakes, but they do happen often, so always check carefully when building your vector. On this slide, we summarize the role of the force vector in the stiffness method. The global stiffness equation is only complete when we include the load vector. Nodal forces are straightforward. They're applied directly into the global force vector in the correct degrees of freedom. Member loads, though, such as distributed or point loads along an element, cannot be applied directly. Instead, we convert them into equivalent nodal forces and moments so that they can be included consistently in the system. Throughout, it's essential to maintain consistency with the degree of freedom numbering and with a sign convention. This ensures that the assembled stiffness equation K times D equals F is both mathematically correct and physically meaningful. Now that we've developed the theory of the force vector, we can move on to coding it. We'll use MATLAB, but the code is identical in Octave. The aim here is not to become programmers, but to understand how the stiffness method translates into a simple structured script that can be reused. In this lecture, we'll build on the code we developed earlier for assembling the stiffness matrix of beams and frames. The structure of the program will feel familiar, but now we extend it to include element rotation, which is essential for analyzing frames in 2 dimensions. Because of this, some terms in the stiffness matrix are added and others are shifted compared to the simpler truss or beam case we coded. The main focus of this lecture is the force vector, how we set it up, how external loads are represented at the nodal level. To make this clear, we will work through a complete frame example, showing step by step how to code both the stiffness contributions and the load vector so that we can solve the system consistently. The first step in the script is to make sure we're working in a clean environment. Clear removes all variables from memory so we don't accidentally reuse something from a previous run. Close all closes any open figures or plots, and CLC clears the command window so we start with a blank screen. These three commands together give us a fresh start every time we run the program. A small but important point: ending a line with a semicolon means the command executes but the result isn't displayed. This is useful for keeping the command window tidy, especially when working with large matrices. With the environment ready, the next step is to define the geometry of the structure, starting with node coordinates. To make the coding process clear, we're going to work through a specific rectangular frame example. Using an example helps us link each line of code to something real. The frame shown here is a one-bay on one-story frame with a span of 6 meters and a height of 3 meters. The frame is a steel frame with a square cross-section of 20 millimeters. There's a vertical point load of 20 kilonewtons at node 3 and a UDL along element 2 between nodes 2 and 3. The UDL is 10 kilonewtons per meter. Therefore, the frame has 4 nodes arranged in a rectangle. Node 1 at the bottom left will designate as 0, 0, node 2 directly above it at 0, 3, node 3 across the top right at 6, 3, and node 4 directly below node 3 at 6, 0. We captured the geometry in the code coding array. Each row lists the node number followed by its x and y coordinates. The distances from the diagram are therefore directly encoded into this array, 3 meters in the vertical direction and 6 in the horizontal. We can also calculate the number of nodes with num nodes equals size coords, 1. The size command counts the number of rows in any array, which is the same as the number of nodes. In this frame, it'll give 4. Next, we tell the program how the nodes are connected to form elements in the elements array. Here, each row lists the element number, the start node, and the end node. So, element 1 runs between nodes 1 and 2, element 2 between 2 and 3, and so on. This connectivity table defines the skeleton of the frame. Finally, we can count how many elements there are with the size command. It'll count how many rows are in the connectivity table, in this case 3. This gives us the number of members in the frame, which the program will later use when looping over elements. We can then define the number of degrees of freedom per node, which for a 2D beam or frame element is 3, as we know. Finally, we assign degree of freedom numbers to each node. This loop creates a table of degree of freedom numbers. For node 1, the degrees of freedom are 1, 2, 3, for node 2, 4, 5, 6, for node 3, they're 7, 8, 9, and for node 4, they're 10, 11, 12. This numbering system is essential for assembling the global stiffness matrix and the global force vector. It ensures that every element knows exactly where its contributions fit in the overall system, and you can see the results for the frame here. With the geometry and connectivity set up, the next step is to define the material and section properties of each element. These properties are what determine how stiff the frame is and how it responds to loads. Here we define Young's modulus E0. A typical value for steel is about 200 gigapascals, which is written here as 200 E9. The next line creates an array E, so every element has the same modulus. If we wanted different materials for different members, we could change this array to store different values. Next, we input the cross-sectional area. In this case, each member is taken as a square section of 20 millimeters by 20 millimeters. Multiplying them gives the area, which is 400 millimeters square. The 1e-6 converts the square millimeters into square meters, giving an area in SI units. Again, the array A assigns the same value to all elements. And finally, we calculate the second moment of area I, which controls the bending stiffness of each member. For a square side of 20 millimeters, the formula is h to the power of 4 divided by 12, or in our case, 20 to the power of 4 divided by 12. The 1e to minus 12 converts from millimeters to the power of 4 into meters to the power of 4. The array Ix stores the value for each element, again assuming identical members. So at this stage, the program knows the material stiffness, the cross-sectional area, and the bending stiffness for every member in the frame. Now that we know the coordinates and connectivity of the structure, we can compute the geometry of each element. This step is crucial because it gives us the element lengths and orientations which we'll later use in the stiffness transformation. Here we set up empty arrays to store the results, the element lengths, the cosines and the sines of the element angles, and the actual angle in degrees, mainly for reporting or checking. Then, inside a loop over all the elements, we pick out the 2 nodes that define each element. For example, if element 1 connects nodes 1 and 2, n1 is node 1 and n2 is 2. We then read their coordinates from the coord table, x1 and y1 for the first node, and x2, y2 for the second. We can then compute the change in x and y. From these, the length LE is found using Pythagoras' theorem. The direction cosines c and s are then just the ratios of differences to the length. So c the cosine equals delta x over L, and s the sine equals delta y over L. These describe the orientation of the element in space. Finally, we store the computed length and orientation for the current element in the arrays. The optional atan2d command gives the angle in degrees measured counterclockwise from the positive x-axis, which can be useful for checking or reporting results. So after this loop is complete, we have for every element its length, cosine and sine of its angle, and its actual angle. This information will go straight into the element stiffness matrix calculations. Now that we know the geometry and properties of each element, we can calculate the local stiffness matrix for each member. This matrix represents how the element resists axial and bending deformation in its own local coordinate system. We first create a 6x6 times the number of elements array to store the local stiffness matrix for each element. Each 2D beam or frame element has 6 degrees of freedom, 3 at each node: horizontal displacement, vertical displacement, and rotation. Inside a loop over the elements, we calculate the parameters for that element. LE is the length from the geometry step. EA is the axial stiffness, modulus times area. EI is the flexural rigidity, modulus times second moment of area. We then explicitly give the standard 6x6 stiffness matrix for a 2D frame or beam element, combining both axial, shear, and bending effects. The EA over LE terms along the top left and bottom right corners capture the axial stiffness. The terms EI over LE to the power of 3 and EI over LE squared and EI over LE represent bending stiffness contributions, shear forces, end moments, and rotational stiffness. The signs reflect how the forces and moments act in opposite directions at the two nodes. And finally, we save this stiffness matrix for the current element into our storage array. After this loop, we'll have a 6x6 stiffness matrix for every element in the frame, ready to be transformed into the global coordinate system. So far, we've built the local stiffness matrix for each element. The next step is to rotate these matrices into the global coordinate system, because the entire structure is assembled in the global xy axes. We start by pre-allocating storage. KLM will hold the global stiffness matrix for each element. TLM stores the transformation matrix for reuse later, for example when transforming loads or recovering local forces. Inside the loop, we pull out the direction cosines, C and S, which describe the element's orientation. This is the 6x6 transformation matrix for a frame element. The 2x2 blocks in the corners rotate the translational degrees of freedom for each node. Notice that the diagonal entries for the rotational degrees of freedom, the ones in the middle of the matrix, remain unchanged. And that's because a rotation around the z-axis in local coordinates is exactly the same as a rotational around the z-axis in the global system. Rotations do not need to be transformed. We save this transformation matrix for later steps. Finally, we rotate the local stiffness into global coordinates using the familiar relation. K global equals T transpose times K local times T. This gives each element a stiffness contribution in the global XY system, which is what we need for assembly. Here on the slide, we can see element 2 for the results as an example. Now that each element's stiffness in global coordinates is known, we can combine them into one system matrix for the whole frame. First, we compute the total number of degrees of freedom. For a frame, each node has 3 degrees of freedom. So the n-DOF total equals 3, the number of degrees of freedom, times the number of nodes. We then initialize the global stiffness matrix K as a square matrix of that size. The option memloc array is just a handy log. Each row will store the 6 degrees of freedom indices, 3 per node, associated with an element, which can be useful for debugging or inspecting assembly. We then write a loop that goes over each element in turn. In the loop, we read the 2 node numbers of the element, E. Using the degree of freedom map, N, which we built earlier, we collect the global degree of freedom indices for those nodes. For frames, this is 6 entries per element: U1, V1, theta 1, U2, V2, theta 2. Storing EDOFs into memloc is optional, but it lets you quickly verify the indexing if something looks off later. The last line in the loop is the assembly step. We add the element's global stiffness contribution, KLM, into the corresponding rows and columns of K. If two elements share a node, their contributions accumulate on that node's degree of freedom. This is the stiffness method superposition principle in action. As with trusses, K remains symmetric. After applying boundary conditions, it'll be positive definite for a stable when well-constrained system. The key difference from the truss case is simply the size of the degree of freedom block. We add a 6x6 instead of a 4x4 because frames include rotations and bending. Here we can see the assembled global stiffness matrix for our frame example. It's a 12x12 matrix because we have 4 nodes, each with 3 degrees of freedom. That gives 12 unknowns in total, so the total global stiffness matrix has 12 rows and 12 columns. Notice a few important features. The matrix is symmetric as expected in structural stiffness formulations. Large values appear on the diagonal, representing the direct stiffness of each degree of freedom. Off-diagonal terms show the coupling between degrees of freedom, for example, between translations and rotations at connected nodes. You can clearly see contributions from bending stiffness. These were not present in the simple truss matrix we saw earlier. At this point, the structure's geometry and material properties are fully embedded into this single global matrix. With the stiffness matrix complete, the next step is to build a global force vector, F, which contains all the external loads acting on the structure. The program is set up to handle 2 kinds of loading. Type A, which are direct nodal loads in the global coordinate system, so horizontal forces Fx, vertical forces Fy, and nodal moments Mz. And Type B, which are uniformly distributed loads, or UDLs, on elements. These are converted into the equivalent nodal forces and end moments, as we discussed in this lecture. We begin by creating a 0-column vector, the same length as the total number of degrees of freedom. This acts as a blank template, which we will then fill in the entries where loads are applied. We then define any loads that we have. In our case, using the example that we've been going over, we have the first row of 3, 0, minus 20, E3, and 0, which means that at node 3, we apply a vertical force of minus 20,000 Newton, negative because it's going downwards, corresponding to a 20 kilonewton vertical point load in the negative y direction compared with our positive degree of freedom definitions. Next, we define uniformly distributed loads. These act perpendicular to an element's axis, expressed in the element's local system. Each UDL row is the element index and then the load, the UDL, where Wy is the load intensity in Newton per meter along the local plus y axis. So, like in our example, a downward load on the horizontal beam is negative. So we have 2, because the load is on element 2, minus 10 E3, which means that we're applying a negative 10,000 Newton per meter UDL to element 2, which is the beam member. And finally on this script, you can see 2 safeguard lines. They ensure that the script still runs if no loads are specified. So in that case, the variables are treated as empty, meaning that no loads of that type are added to the global force vector. In the next step, we loop through the list of nodal forces, 1 row at a time. Each row should contain 4 values: the node number, the horizontal force, the vertical force, and a nodal moment. For the current row, we first read off the node number and then extract the 3 load components associated with that node. Next, we need to place each of these in the correct location in the global force vector F. To do that, we use the mapping array N, which we already defined previously, and this tells us the global degree of freedom numbers for each node. For example, the first column of n gives the degree of freedom number for horizontal displacement, the second gives the degree of freedom for vertical displacement, the third gives the rotation. So for this node, the horizontal force goes into degree of freedom for horizontal displacement, the vertical into vertical, and the moment into the one for rotation. If 2 loads act on the same degree of freedom, they simply are added together in the vector. By the time the loop finishes, every nodal load has been correctly inserted into the global vector F, aligned with the degree of freedom numbering we used for the stiffness matrix. In our example, once the loop is completed, the global force vector will look like this. You can see here at degree of freedom 8, which is row 8, we have minus 20,000 newtons. In this part of the program, we assemble the uniformly distributed loads. The loop goes through each row of the UDL table, which tells us which element the load is applied to, and the load intensity, Wy, which is defined in the local y direction of that element. For the chosen element, we first calculate its length, and using this we work out the equivalent nodal forces and end moments that represent the effect of the uniform load. In local coordinates, each end of the member carries half of the total vertical force, and each end also carries a moment of the magnitude of Wy L squared over 12. The signs of these nodal forces and moments follow the element's local axes and the standard stiffness method sign conventions. A positive Wy acts along the positive y, so it's upwards if the element is horizontal, and a negative Wy acts along the local minus y, so downwards if the element is horizontal. The end moments are opposite in sign at the two ends, producing the correct bending effect. Because the loads are defined locally, we must rotate them into the global coordinate system. We do this using the same transformation matrix that was used earlier for the stiffness matrices. This ensures that whether the element is horizontal, vertical, or inclined, the equivalent loads are expressed consistently in global x and y. And finally, we map these global loads into the overall force vector F using the global degree of freedom numbers of the two end nodes of the element. If more than one element contributes to the same degree of freedom, the effects are added up. By the end of this loop, every distributed load has been converted into nodal forces and moments, rotated into the global axis, and placed in the correct positions of the vector F. In our worked example, the global force vector contains non-zero entries only at nodes 2 and 3, where the loads are applied. Node 2 carries a minus 30 kilonewton vertical force and a minus 30 kilonewton meter end moment from the left half of the beam UDL, and node 3 carries a minus 50 kilonewton vertically, made up of the minus 30 from the UDL and the minus 20 from the point load, along with a plus 30 kilonewton meter end moment from the right half of the beam UDL. All other degrees of freedom remain zero as no loads act there. This confirms that both nodal and distributed loads have been assembled consistently into the global vector. At the end of the program, we output the key results so that we can inspect and verify them. First, we change the display format to engineering notation, short eng. Engineering notation always uses powers of 10 that are multiples of 3, and that makes the numbers easier to interpret in structural engineering. fprintf is used to print labeled headings like global stiffness matrix. Display then shows the actual contents of a variable, like the whole matrix or vector. In this case, we display the global stiffness matrix K, which in our case is a 12 by 12, the element lengths and angles, which confirm the geometry has been calculated correctly, and the complete global force vector F. Although we've shown this code in MATLAB, it'll also run directly in Octave, which is a free open source alternative. Octave uses almost exactly the same syntax as MATLAB, so you can just copy and paste this script, and it'll work exactly without changes. This means that you don't need a paid MATLAB license to practice. Octave is available to download and use at no cost. And this makes the stiffness method coding exercises fully accessible whether you have MATLAB installed or not. So no excuses. Thank you for joining me. In this session, we have nearly completed our analysis of a beam or frame element using the stiffness method. We've now put everything together, created the local stiffness matrix, rotated it into global coordinates, and pulled in all the element stiffness matrices to complete a global stiffness matrix for the whole structure. We have now also added the force vector. So join me next time because we have all the ingredients to solve the stiffness equation. We'll do that together next time.